Okay, so the next thing that we have here is about basically the measurement of length. It's about the measurement of length. So basically there are basically different ways of measuring length. There are direct methods. There are direct methods of measuring length. For example, you can use a meter scale or a meter stick. You can use a meter stick to measure length, right? Or, for example, you can use, for example, vernier calipers in order to measure length if you need more basically more precision. Or basically you can use something called a screw gauge. So Gauge, which is basically called a screw gauge. No, a screw gauge is still used for basically for measuring length, but very fine lengths. And there is also something called a spherometer. A spherometer, right? And these are basically all direct methods, meaning that you actually have access to what you want to measure, and so you can measure them. Now, what happens is that when you want to measure large distances, for example, the distance between the Earth and the Sun, the Earth and the Moon, and so on and so forth. So of course you do not have access to those distances, and you cannot put a meter stick basically between the Earth and the Sun and measure the length. It's going to take you forever, first of all, and second of all, it's not even going to be possible. So in such cases, basically we use something called the parallax method. We call the parallax method. Now, the parallax method basically works based on the fact that, it's actually not a fact, but it's basically how observing basically takes place in nature, basically. Meaning that, for example, suppose that you're reading, for example, a voltmeter. Now, a voltmeter, an analog voltmeter like this, you would have a scale over here. You would have some scale over here, and you would read. This would be a needle on your scale, and this needle keeps moving on your scale, and here you have some basically wires and so on and so forth. So basically there is some distance between this needle and the background, or there is basically a plate behind the needle. On this plate there is all of these numbers, and you have to read basically the needle against these numbers, and that way you can make a reading. Now if you try this, you will notice that basically well, since there is this slight distance of 1 or 2 millimeters between the needle is a little bit raised with respect to the background, which is enumerated. Okay. So because of this tiny distance, what happens is that when you suppose that the needle, for example, comes all the way up to this point, and now you want to read it. Now, behind the needle on this area, there is all numbers basically printed beside one another, and the numbers are very close, or at least the graduations are very close. So if you look at this needle from the right, you're going to see basically you're going to make some reading. If you look at the meter from straight from the top of the meter, you're going to make some other reading. If you look at the meter from another angle from the left, you're going to make another reading. Meaning that depending on how you're looking at, depending on from which point basically you're looking at the needle, your reading is going to be different, meaning that the point on the background that you see is going to be a different point depending on the point from which you look at the needle on top of the background. And you can basically do the same experiment using, for example, a pen in your room, wherever you are. There is, of course, walls. There is no place that a human being lives where there exists no wall. So when you're sitting in your room, you can basically, for example, hold this pen in front of you like this against some wall, and then what you can do is that you can close one of your eyes, okay, and look at the tip of the pen against some point on the wall, meaning that you will see the tip of the pen against some point on the wall if you look through your left eye. Then you can cover your left eye and then look through your right eye, and what you will notice is that basically once you change your eyes, meaning that once you switch from your right eye to the left eye and vice versa, what happens is that basically the tip of the pen is going to be seen against different points on the background wall. And basically so what that means is that, again, the eye is the observer looking at the tip of the pen on the background, which is the wall. And once you change the observer, because the observer in this case are your two eyes, and there is some distance between your two eyes, and because of this distance, then the point that you see on the wall behind the tip of the pen is going to be shifted when you shift your eyes, right? When you switch your eyes. So this phenomenon is called basically is called parallax, right? And in the example that I gave you, related to looking at the tip of the pen from basically your eyes, switching your eyes, there is some, basically, if this is your head, then this is your eye, and this is your eye, and there is this distance over here, and this distance is, if I call it D, this is called the base. This is called the base. Now, meaning that the distance between the 2 points of observation, right? Now, what happens is that basically when you want to measure the distance of a faraway planet, when you want to measure the distance, for example, the distance of a faraway planet from the Earth, what you can do is that you can use the parallax method. And the way that you can do it is that suppose that, for example, this is the planet. This is the planet, right? I call it S, for example. And then you can imagine that the planet is something like this, and then you have to basically you can think of this as some point A and some point B here. These 2 points are 2 points of observation, or basically we call it observatories. In normal language we call it observatories. That these are places where you can go and look at the sky and see different stars and so on and so forth. So these are 2 observatories on the Earth, and this is the planet. So you have to basically look at the planet simultaneously, and meaning that no time is supposed to pass between the 2 observations, because, as you know, in the universe everything is moving. So if you give it even half a second, then everything has moved, so your calculation and everything will be, well, at least to some extent wrong. So you have to look at the planet from these 2 points simultaneously, and then note the basically depending on the type of the telescope that you're using, you're going to get some angle over here, and you're going to get some angle over here, and then based on, you have to use some geometry, and based on the 2 angles that you have found here, you will find some angle over here and some angle over here on your telescopes, for example, you can imagine. And based on these 2 angles, you can calculate this angle. Let's call it theta, right? Now, what happens is that when we define the radian angle measure, we said that if we have a circle like this, and we defined 1 radian as basically some, for example, we said that if this is O, the center of a circle, and this is the radius of the circle, and this is some arc related to the circle subtending this angle theta, this central angle theta, we said that if S divided by the ratio of S and R is equal to theta in radians. So the angle, this angle theta, the measure of this angle theta is the ratio of S and R in radians, of course, not in degrees, but in radians. So as you can see, these 2 look exactly the same. These 2 figures look exactly the same, except that this is an arc, and this is just some distance between the 2 observatories on Earth, and that is just a straight path between A and B. Now, what you can do is that, and this is basically the distance between the Earth and the planet. You can call that D. And for example, you can call that B. Now, what you can do here is that basically B divided, basically B divided by D, if I take the ratio of B and D, B basically relative to D, B is very, very, very small. It's just some distance on Earth, and the distance between, for example, Earth and some planet would be in the order of 10 raised to the power 8, 10 raised to the power 9 meters, for example, or something like that. And this would be, for example, 5,000 kilometers or 2,000 kilometers or something like that. So it's actually just simply nothing compared to this distance. So since B compared to D is very small, this ratio B to D is going to be very much less than 1. It's going to be a ratio very close to 0. And therefore, you can, of course, you know that basically you can conclude that theta is going to be a very small angle, because this would be a long side of a triangle, and this side of a triangle relative to this side would be a very tiny side, basically. Now, since this distance B is very tiny, it doesn't really matter whether you take it as a straight path or an arc. An arc is a curved path, and well, normally it has to be, it is of course a straight path, but it doesn't really matter whether you take it as a straight path or an arc, which is a curved path, because at the end of the day it doesn't make any difference really. B is very tiny relative to D. And so basically what you can do is that if I imagine that this is instead of basically this straight path, if I imagine that this is an arc of length B, I can simply say that basically this arc B, and so then this would be a sector of a circle, of course. And then I have I have this length B, and I have this length D, and I have this angle theta in that circle. And so based on the definition of the radian angle measure, we said that B divided by D, D is the radius of the circle, B is the arc length, is equal to theta in radians, right? So which gives us basically AB, which gives us basically B is equal to, if you cross multiply here, you will get B is equal to D theta, right? Or you can say that D is equal to B divided by theta. All of these are basically the same relationship. Now, so this way, you know, basically you already know the distance between these two observatories. So that means that B is known. And based on the two angles that we basically, when we wanted to look at the planet from these two observatories, we could basically, so assuming that the two telescopes have basically are basically can calculate the angle for you, then you have access to this angle as well, meaning that this theta is also known to you, right? And therefore D can be calculated, meaning that the distance between the Earth and the planet can simply be calculated. Now once you do this, once you have determined the distance of the planet from the Earth, you can use a similar method to determine the size or angular diameter of the planet as well. So now you can say that having determined D, now you can determine the size. The size means the diameter, of course. You can determine the size or the angular diameter or the angular diameter of the planet. And I will tell you what they mean by the angular diameter. Now, what is meant by this? Now that you know that you know the distance between the planet and the Earth, now you can suppose that, for example, here you are, for example, on Earth somewhere over here. So let me draw a circle over here, and draw a circle over here. So I'm going to, so if suppose that this is a circle over here, and I'm going to go select the border, and over here I'm going to do a circle as well, and go select the border. Now I have these two circles, right? And suppose that this is the Earth and this is the planet. And now you know the distance between the two. Now, for this, basically, in order to find the distance, the diameter of the planet, or the angular diameter of the planet, you do not need to look at the planet from two different points. You can imagine that, for example, you can take a look at the planet from this point. Of course, there is a problem with this method, and I have seen this problem before. You see, if I want to, suppose that I want to take a look at any diameter of this planet, for that matter, it's just not possible to do it, because the planet itself, the edges of the circle are going to get in the way, and so you have to find some way in order to actually, you have to use some indirect method using, for example, mathematics, in order, and use the properties of circles and geometry and things like that in order to do that. Otherwise, for example, suppose that my telescope is over here, exactly at some let's say some point on the surface of the Earth, and I want to look at the edge of this diameter here, and you can see that my line already goes over the edge of the planet, and I'm not seeing that point really. And so I can do the same thing over here, and what that means is that now from the exact same point, I have to take a look at one end of the diameter, and then again take another look at the other end of the diameter, and then based on that I will get some angle theta here, right? This angle theta here, and I have this d over here, which I have already calculated from the previous step. And therefore, if now I imagine that this is, instead of a straight path, if I imagine that this is a curved path, an arc of a circle, then I can say that, for example, this is, for example, if I call it B, for example, then I can say that, then I can imagine that this part over here is a circle, and this is the arc of the circle, this is the radius of the circle, and this is the central angle of the circle. And again, based on the definition of the radian angle measure, I can say that B divided by D is equal to theta in radians, of course. D is known to me, B is not known to me, so B is equal to d theta, right? B is equal to d theta, and I know theta, I know d, and that way I can calculate the angular diameter of the planet, meaning that I will know how large the planet is, or something like that. So but the method is of course in and of itself is of course it works, provided that you do some, that you get around the edges here, and you can take a look at the edges, because basically no matter what you do, you're not going to see the edges of the diameter. You're going to see, for example, this point here, not this point. This point you're not going to see, or you're going to see, for example, some point like this. No matter where you place your telescope on the Earth, you're not going to see the edges of the diameter. So, but I'm sure there is some way in geometry or in mathematics that you can get around that problem, and they must of course have actually done it in some way. Otherwise, the parallax method is a real part of astronomy and physics, of course. So now this is of course not that important for us right now. What we need to do is that we need to learn some angle conversion. Because there is always these problems that you need to be able to do some angle conversion. And I suggest that you write down, basically for this problem, you can write down your values over here on a piece of paper and keep it, because you are going to need it in different problems.